Okay, so I'm going to go over some content for us covering 9.1. Hoping that you can go through this video and spend some time, maybe take notes as you go, and then you'll be able to work through 9.1 on a regular schedule. We'll probably do a little bit of it in class, depending on what happens with the weather the rest of the week, but it'll be an accelerated in class, as I will assume that everyone has the opportunity to go through the video. So to get started, move myself out of the way. There we go. And what we're looking at is chapter 9, which is solving quadratic equations. And remember, a quadratic equation has the highest power of 2 on the variable. 9.1 has two topics, solving perfect square equations using square roots and solving by a method called completing the square. So again, a quadratic equation, the highest power of the variable x is 2. And we're going to look at solving perfect square equations using square roots. A perfect square quadratic is one where there is some quantity squared but has no x to the first term. It has no x term. So we could look at an example that says, which of the following are perfect square equations? X squared plus 3x equals 12. X squared minus 8 equals 17. The quantity x minus 3 squared equals 16. 5t minus t squared equals 12t plus 10. And again, it would be good if you could take notes. So if you need to pause anywhere during the video, go ahead and pause, write that down. And which of these are perfect square equations? Any equation where it just has a quantity squared and no x to the first term. So the first one is not, because it has an x right here. So no. The second one is, there's no x term and it has an x squared there. Third one is also a perfect square because it has a quantity x minus 3 squared and there's no other x term floating around. And the last one is not. It has several t terms, one there, one there. So no. So in both these equations, because there is no x term, we can use square roots to eliminate the squared term. So we have to be a little bit careful here because unlike chapter 8, we can no longer assume that the variables must be positive. So we had made that assumption in chapter 8 when we were reducing square roots, but we can no longer do that when we're solving these quadratic equations. So to do this, we're going to use the fact that instead of having the square root of x squared equaling x, we're going to recognize that the square root of x squared is actually the absolute value of x. That will guarantee a positive value when we take the square root. So the square root of x is the absolute value of x. This is how we'll get rid of the squared quantity, but then our equation will have an absolute value in it, and we'll have to figure out how to remove that. So first, I want to look at how do we solve a few absolute value equations, because this is going to come in after we've square rooted. We're going to have this absolute value that we're going to need to get rid of. So for example, if I have the absolute value of x equals 3, what does that mean? That means the distance that x lies from 0 on the real number line is 3. So think about, what numbers are 3 away from 0? Well, if I draw the real number line, we can go 3 in either direction, 3 to the left or 3 to the right. Both those numbers are 3 away from 0. So the solution to the absolute value of x equals 3 is that x equals -3 or x equals +3. In some cases, we will combine these solutions. I will generally only combine them when they involve a root or an imaginary component. But just so we can see the notation, I could combine these together and write more succinctly that x is equal to ±3. And I just have that suggestion down here that says, let me make this a little bigger. We will generally only use the plus and minus notation. Actually, it's plus or minus when it precedes a term with a root or an imaginary factor. Okay, so I'm going to look at how to solve a few absolute value equations. Myself out of the way here. The first one is the absolute value of x equals 12. There's no root here, so what I'll do is I'll branch this into two solutions. Who's 12 away from 0? Branch it out. On the negative side, it'll be negative 12. X equals negative 12. Or on the positive side, it'll be x equals 12. Again, you might want to take notes on these problems as we go. Then you'll have record of it when you want to come back and do the homework. The absolute value of x plus 3 equals 12. So now we have some quantity inside the absolute value equaling 12. But the solution process will be the same. We need to remove those absolute values once they're isolated. So whatever the quantity is inside the parentheses, in this case, x plus 3, is 12 away from 0. So it either is located at negative 12, or the quantity inside the absolute values, x plus 3, is 12 to the right of 0 at 12. And now, when we solve these equations, this step should be the same. Those parentheses can be ignored. And I just put them in to sort of group the x plus 3. And to solve them, we subtract 3 from both sides. So here I'll get x equals negative 12 minus 3 is negative 15 on the left. Or if you take away 3 from 12, x equals 9. And if we plug negative 15 and 9 back into the original equation, we'll see that it's true. In the next example, myself over here for a second, the absolute value of 2x minus 1 equals 9. Oh, I should mention here, ideally, these videos are best watched on a computer. If you're watching on a phone, it's very hard to see the math. And similarly, it's like you're just watching someone do the work as opposed to doing the work with them. So ideally, you have a computer running and you're taking notes as we go. Here we have the absolute value of 2x minus 1 equals 9. I've done already isolated the absolute values in all of these. So once we get to this step in the process, we can break this up into two equations. Whatever is inside the absolute value, 2x minus 1, on the left will equal negative 9, and on the right will equal positive 9. And you'd think that the answers will be plus and minus of each other. They're not. These results are plus and minus of each other, the 9 and negative 9. But then when we solve these two equations, so here I need to add 1. This process of adding 1 should be the same in both of these equations. In other words, we don't change the 2x minus 1. We don't change the thing inside the absolute value. So on the left, we get 2x equals negative 8. And on the right, we get 2x equals 10. Divide everything by 2. And we get two solutions. X equals negative 4, or x equals 5. So notice they're not negatives of each other. They're slightly different because it's not that x is a plus and minus, it's that 2x minus 1 is a plus and minus 9. So this is one of the reasons why I would like to break up into two solutions when I don't have a root. When I do have a root, sort of like this next one, absolute value of x plus 1 equals the square root of 5, I'm going to do it both ways and show you why we leave it using the plus and minus notation. So first off, if I broke it up, I would get x plus 1 on both sides, because that's inside the square root, inside the absolute value, and it would equal negative root 5 on the left, and it would equal positive root 5 on the right. And then we would need to subtract 1 from everything here. And because 1 and root 5 are not like terms, we would put that negative 1 in front. And here I would get negative 1 minus root 5. And here I would get, and I'm adding those, so negative 1 plus root 5. So you can see this notation, we're never going to be combining the 1 with the 5. So in this case, it makes more sense to write this as x equals -1 plus or minus the square root of 5. And really, if we go back to the original equation, in general, when I have a root or an absolute value, instead of branching it out like I have been with a left and a right, I'll just break it up right away with a plus or minus root 5. The reason I don't do this above is because we're getting two separate solutions in general. For example, the previous problem, we got -4 and +5, so they weren't a plus and minus of each other. But in this case, when you have a root, now when I subtract 1 from both sides, I can kind of sneak that run in front here. And on the left, I get x, and on the right, I get -1 plus or minus the square root of 5. And one thing to keep in mind about this answer is it really is two numbers. It's -1 plus the square root of 5, and it's -1 minus the square root of 5. Okay, good. So that's solving square absolute value equations, and we're going to need that to solve the perfect square quadratic equations. So going back to our example, we had a couple that were perfect squares, x squared minus 8 equals 17, and the quantity x minus 3 squared equals 16. So both of these are perfect square equations because they don't involve a single x term, or in other words, they just have something squared. Okay, so I want to do the first one. The process I've written down already. We recognize it's a perfect square equation. Then we're going to isolate the squared term. In this case, add 8 to both sides. Oh, my pen's gone crazy there. Come on. So adding 8, we get x squared equals 25. So I isolate the squared term. Then I'm going to square root both sides of the equation. So that square root we were hoping is going to get rid of the square. It is. But on the left, so on the right, I know what the square root of 25 is. That's 5. We know that from chapter 8. And in chapter 8, we treated the square root of x squared as x. But now, because I can't assume that x is positive, I don't get an x. I get to get, instead, an absolute value of x. So this is the tricky part. I get this absolute value equation that x equals, the absolute value of x equals 5. Okay, and so now we introduce that absolute value to get rid of the square. And then we want to get rid of the absolute value. So if I don't have a root, but here I don't, I'll break this into two equations. The left being a negative value, and the right being a positive value. So x equals -5, or x equals 5. So again, in the process, first recognize it's a perfect square. Something's going on with my pen, sorry. Then, oh well, it's okay. Then isolate the squared term, square root both sides. When we square root both sides, we introduce an absolute value equation. We have to remove those absolute values, either branching it out into two solutions or using the plus or minus when you have a root, and then you solve the resulting equation. Okay, so I'm going to go to the next one. The quantity x minus 3 squared equals 16. So step 0, isolating the root is done. Or step 1. Step 0 was, sorry, to make sure it's a perfect square. It is. Step 1 was to isolate the thing that's being squared so that we can square root both sides. So I'm going to square root both sides here. By taking the square root of the left equals the square root of the right. If I look at the right side of this equation first, it's a little easier. we know what the square root of 16 is. It's 4. On the left, I'm taking the square root of something squared, and I can no longer make an assumption that that thing is positive. So I need to add in these absolute values. And I'll get the absolute value of x minus 3 equals 4. If you're watching Derek Madison's videos, probably this step is not shown, and he'll go right to the plus and minus, but it's safer to show this step to understand where the plus and minus is coming from. So we're going to get an absolute value equation in step 3, and then how do we remove those absolute values? Well, we're either going to use the branch when there's not a root, or the plus and minus when you have a root or an imaginary value. So in this case, we don't have a root on the right, we have a 4, so I'm going to branch it out. Whatever's in the absolute value, in this case x minus 3, is going to equal -4, or whatever is in the absolute value x minus 3 is going to equal +4. After you break it apart, the process of solving these equations should be the same. So the step that I'm doing here, adding 3, I can do it to both equations at the same time, and that's kind of allows a little checking mechanism that I didn't change the signs on the thing inside the absolute value. Here I get x equals -1, or x equals 7. And you could do a quick mental check. If I plug in -1 upstairs in the original equation, -1 minus 3 is -4. And if you square -4, -4 times -4, you get 16. So the mental check there works. We don't need to do the mental check, but sometimes it's helpful to see why the two answers both work. The other one, 7 minus 3 is 4, and you square 4, you get 16. So we did a mental check there. Okay, last one. On this set, I think, maybe I have one more below it. Yep, I do. The next one then. Again, is it a perfect square quadratic? Yes, because there's only a t squared. There's no middle t term. So I need to isolate the t squared, or the thing that's being squared. I can do that by subtracting 2. And get 1/2 t squared equals -2. And then I'll multiply everything here by 2, or 2 over 1, to get rid of this 1/2. And give us t squared equals -4. The reason I isolate the square is so that I can square root both sides. When I square root both sides, I'm going to get an absolute value equation. So I just write this step down so that I remember that I'm getting this. And this is new for most of us, absolute value equation here. So what are we going to get here? Well, what's the square root of -4? This is why we studied imaginary numbers in chapter 8. The square root of -1 is I, square root of 4 is 2, so that's going to give me 2i. On the left, we have the square root of t squared. We'd like to say that's t, but it's not. It's the absolute value of t. So now we have the absolute value of t equals 2i. Because I have the imaginary value here, I need to either use a branch that creates 2 solutions, and they both create 2 solutions. The branch has written separately, the plus or minus has them written together. Because I have an I here, I'll use the plus or minus to get rid of the absolute values. You can kind of think of these guys as the absolute values are disappearing, and they're becoming this plus or minus in this case. In the other case, the absolute value disappears and becomes the branch, left and right. T equals plus and minus 2i. Again, feel free to pause if you need to copy that down. I'll scroll ahead. The next one. Is it a perfect square quadratic? It's quadratic because there's an x squared. If you were to multiply this all out, in fact, there would be a 4x squared, but there would be an x squared, so that makes it quadratic. You could multiply this all out and it would no longer be a perfect square, but in this case, we have a quantity 2x plus 1 squared with no other single power x to the first term. So we have a perfect square quadratic. We're going to isolate the thing being squared, which is the 2x plus 1, by adding 8. We get 2x plus 1 squared equals 8. The only way the square root undoes the square is if you are, if you have that square isolated. So then we can square root both sides, which, since I'm over here, will create an absolute value equation. So those symbols, those two vertical bars, absolute values. Okay, so square root both sides. Square root of 2x plus 1 squared equals square root of 8. I generally like to reduce the right-hand side of this equation first because that's what we did in the last chapter. Square root of 8, 8 is 4 times 2, so this is 2 times the square root of 2. On the left-hand side, we have the square root of something squared, producing an absolute value equation. In this case, the absolute value of whatever is inside the root, 2x plus 1. And then to get rid of the absolute values, I'm going to either use a branch or a plus or minus to remove them. And because I have this root here, I'm going to use the plus or minus. So equals, and I'll remove the absolute values by putting in a plus or minus. When you do these steps, I would suggest you do it sort of similarly in that you don't just jump from the square, this step, to that step. You can, a lot of texts will. I like to put the absolute value step in. It helps us understand why we're getting plus or minus. We get two solutions out because there's a positive branch and a negative branch. Okay, and then now because I have this root, I'll use the plus or minus. Makes it easier here when I subtract 1. I put that 1 in the front of the plus or minus, and I get 2x equals, well, in this case, it's a negative 1 in front. Negative 1 plus or minus 2 root 2. And then we divide everything by 2. And we get x equals, this is our answer. We could leave it like that. Plus or minus 2 root 2 over 2. So a little bit of weird on the homework. That's fine for me. That's a perfectly good answer. On your homework, if it has an imaginary solution, this is how they were going to leave it. The I is going to be filled in for you, as is the plus or minus. So I think imaginary solutions will look something like this on homework. In the XYZ. And if this one were imaginary, then the first box would be a negative 1, the second box would be 2 root 2, and the third box would be a 2. When it does not have an imaginary solution, it's not going to use the plus or minus notation. Sorry. It's going to, why can't I undo it? Parentheses divided by 2, or negative 1 plus 2 square root 2 in parentheses divided by 2. It's weird, it erased the box thing for the imaginary solution, but it didn't erase the scribble marks. Okay, so that is solving quadratic equations when you have a perfect square. And it's the first part of 9.1. Again, the process, identify that it's a perfect square equation, isolate the squared term, square root both sides. That produces an absolute value equation. Remove the absolute values using the branch to get a positive and a negative value like here, or the plus or minus when you have an imaginary solution or a root. Okay, so the next step, the next thing that we're going to look at is solving quadratics by completing the square, and I'll do that in a separate video.